figure out areas underneath curves or between curves. What we'll show in this video is that you can actually use pretty much the exact same principles to figure out the volumes of rotational solids. So what do I mean? So let me just draw a couple of examples. So let's say let me start with a fairly straightforward function. That's my y-axis. This is my x-axis. Let me draw my function. Let's say my function looks something. I'm going to draw y equals the square root of x, but I'll keep it general right now, just to show that this applies generally to a lot of things. So square root of y equals the square root of x looks something like that. Right? It keeps going. Actually, let me redraw that because I didn't want it to curve down like that at the end. So it goes up like that, and then it just keeps going up like that. That's better. Okay, so we'll call that f of x. F of x. This is our x-axis. This is our y-axis. And we already know that if we wanted to figure out the area under this curve between 2 points, let's say between the point A, well, we could do it between any 2 points. Let's say this point A and this point B, and we wanted to find this area between the two curves. I'm drawing everything crooked today. There's a different color. So if we wanted the area, if we wanted this area right here, we would essentially just as a review, be summing up a bunch of small squares where each square has a bunch of rectangles, has a width dx, and its height at that point would be whatever x value here is. It would be f of x, right? And if we take the sum of all of these areas, of all of these rectangles, we would get the area of this curve. And we learned in the definite integral video that that's just equal to the definite integral from a, that's the lower bound, from a to b of f of x times d of x, right? Where each rectangle is f of x times d of x. And hopefully this makes a little bit of intuitive sense to you. I think a lot of people go through calculus just learning how to do it mechanistically, just learning, how to do it like a robot without really understanding necessarily what's going on. And if you understand what's going on, you'll never be really lost when you see something a little bit different than what you might have practiced. So with that out of the way, let's think about something. What if we took this function and we rotated it about the x-axis? So this might take a little bit of visualization, but what you imagine is, let me see if I could draw. So I take this curve, and if I were to rotate it about the x-axis, it would look something like this. It would look like a sideways cup or vase, right? It would look like that, where that would be the opening, right? That would be the opening on the inside. I can even shade it, show you my drawing skills. Okay, hopefully that makes sense. So this was, that would be the y-axis there, and the x-axis, let me draw in a different color. The x-axis would pop out the middle, right? That's if you took this and you rotated it around. So let me draw an arrow to show that we're rotating it around. Rotating around. And if we did that, what would be the volume created by, well, we could say, let's use the same boundaries between A and B. So if we took this piece and we rotated it around, what would it look like between A and B? It would look something like this. Well, it would look, let me see if I can draw it. So you would have a, whoops, I'm not drawing that well. This is really testing the limits of my ability to use this computer to draw things. So you would have, I'm just drawing, it would be kind of a circle on one end, and then it would curve down a little bit. It would curve down a little bit, and it would be another circle on the other end. And then if I were to draw the x-axis would kind of pop out of the middle, right there. That right there would be the point B, x equals B. And then if we were to, let me do it in a different color, if we were to kind of go behind or look into the object, we would see the other surface of this rotational solid, right? And this point right here, that would be A. Let me draw that in a different color because it's hard to see. That'd be A. And then of course the x-axis would keep going, and then that would be the y-axis. Hopefully that makes it. The visualization really is the hardest part about these problems. So first step is actually just to imagine what you're doing. So, and if we were to draw the whole curve, so I just did this section if I rotated it about the x-axis. But if I were to draw the whole curve would look something like this, right? It would look something like that. And we're just rotating it around. Hopefully that makes sense. We're rotating it around that way. So how do we do that? Well, we use the exact same principle. When we figured out the area, we would figure out the area of each of these small squares and then integrate, we would take the sum of an infinite number of infinitely small squares, and we got this, right? So to do the volume, what we do is, instead of having each rectangle, we kind of rotate each of these rectangles around the x-axis. So if this is one of the rectangles, if that's the rectangle, it has width d, let me do a brighter color. It has width dx, right? That's my rectangle. And it has height f of x, right? I'm trying to switch colors. So this height right here, that's f of x at this point, right? If I were to rotate this rectangle around the x-axis, what do I end up with? Well, I'll end up with a disk. Let me see if I can draw that reasonably well. I'm trying to show you some perspective when I draw it. Whoops. So that would be the top surface of the disk. And this would be the side of the disk, right? And so this is the top surface of the disk. And what would be the radius of this disk? What would be this height right here? Well, that radius, that's going to be f of x, right? That's this height. Imagine if you took this and rotated it around, that's the same thing as this height right here, right? So that height, or the radius of the disk, is f of x. And then what's the width of the disk? Well, that's just d of x, right? That's the same thing as this. We just rotated it around. So what would be the volume of this disk? It would be the area of this side. It'll be this area right here times this height. Well, what's the area? Well, we know the radius, right? Area is equal to pi r squared. What's the radius? I keep drawing over things. What's this radius? That radius is f of x, right? So the area of this disk, the area of that disk, area is equal to pi times the radius squared. So it's pi times f of x, the whole thing, squared, right? So what would be the volume of this entire disk? So it'll just be this area times dx. So the volume, I'm running out of space and colors. So the volume of that disk, is going to be equal to area of that disk, pi f of x squared, right? The whole function, whatever length this is at any point squared, that gives us the area, times the depth, you can say, so that's d of x. Now that gives us just the volume of this one disk when it's rotated around, right? So if we wanted the volume of this entire object that I drew here, we would just sum up a bunch of these disks, right? We would take each of these rectangles, rotate them around, figure out the volume of that disk it creates, and then sum them up. And so essentially we have we're going to take an infinite sum of a bunch of these small little disks, so we can take the integral. So this is the volume of each disk. We could call that volume of a disk. So what's the volume of the whole thing? Well, we just take a sum, an integral sum of each of these disks. So the volume, when you rotate it, is going to be equal to the definite integral between, and remember our boundaries were a and b, between a and b, of this quantity right here, pi f of x squared d of x. dx, not d of x, dx. So hopefully that makes sense to you. Just remember, this is the depth, this is the width of each disk, this is the radius of the disk, or the radius of the surface, so we square it, and that makes sense. That's the height, f of x. And we have to pi r squared, so that's where the pi comes from. Some people just memorize that. I don't recommend you do that, and we'll see that later. But I'm out of time. In the next video, I'll actually apply this to an actual problem. See you soon.